Okay, now, so what we did so far was unicast. Now, multicast is similar to unicast. Now, this is how, what is multicast? So let's say I want to turn on all light bulbs in this room. So instead of saying, to one node that turn itself on, I would say to all light bulbs, please turn on. That's a multicast, right? If you are a light bulb, then you send a reply, okay, I am a light bulb and I got it. Okay. And if you're not a light bulb, then you don't respond. So that is what it is. If a node receives a request but is not a member of the group or does not have the route to any member of the group, it creates a reverse route entry and broadcasts to other neighbors. If a node is a member, then it sends a reply to the source and forwards it to other neighbors. That is the difference. Is that if you are a member, you reply first, but you also send to other people that please, there is a request here. If you are a light bulb, answer. Okay. Intermediate nodes make a note of this in both direction, and so everything else is similar, but except that the things just continue, until all the light bulbs are responded. All right. So here's an example. D and E are members. We are to all green nodes. Okay, A sends a member, all green nodes. A will send to B and C, B will send to C, A and D, and C will send to C, B and E and D, right? But the only people who will reply is D and E. D will also send it to, basically in all directions, but it will respond as well. So when it responds, this red thing comes back. And E will also respond when it gets it and will come back like this. And then everybody will make a note of how to reach A and how to reach D and how to reach, and somebody will make a note of how to reach E, C, and things like that.
Okay. So
B2C, there is no red. Can somebody explain why there is no red from B2C? Because there is no, see, thing is, the red things are all going to A, and C knows the best path to A is direct here. Why? How does it know? From the forward direction, it had made a note. When the blue thing came, it made a note that the best path to A is on this link. And similarly, this answer goes only along this path because E knows that it came from C. Right? So there is nothing on these red on these links. Yeah, so same thing. So basically, D, when will D hear first? D will hear when the packet is getting from B to D. So it makes a note that the fastest path to A is via B. So it will send the reply to B and not to anybody else. It will forward the request to E. Actually, what I have not shown is maybe another packet going from E to D. Make a note of that. E to D and D to C. Well, I'm not, I think, let me see, hold on, let me see. Since this is multicast, yeah. Since this is multicast, it will go to in both directions. So D will send back to C and E. And if it is dumb enough, it might send it back to B as well, but I think that would be crazy. It knows that it came from B, so it is not going to send it back to B. But basically, C, it gets from C and it sends to C, E, D, E. So everything else might be two directional here in the blue case. But that's interesting. Yeah, so what actually, there are a few mistakes in this picture. If you remember here, two broadcasts to one, right? And that is very easy to fix actually. When you know that it came from one, why am I broadcasting it to one, right? But this is what they decided, to just not remember where it came from, right? So this blue probably should go back here to A as well, if it doesn't remember where it came from. But I think that is very easy to fix. So either we fix it in the previous case, or we fix it here. In here, we put the reverse broadcast as well. Or B to C and C to B? Yeah, no, but that would be an optimization which they decided not to do. See, the thing is, this is very easy. I mean, so there are many flooding protocols, okay? And in every flooding protocol, the designers decide whether you send it backwards or not, okay? It just requires keeping track of where it came from and then not at least sending it backwards, right? And that that here, because they have a sequence number, they decided not to keep track of that, and the sequence number, the destination will discard it rather than my not sending it. So you send it backwards, and then it will be dropped at the first hop, right? So they decided that, and that's what we said in the previous whole example here. It goes backwards, right? If that is the case, then B should go backwards. The blue packet should always be bidirectional. Only the red packets are unidirectional. Yeah, no, not whole cycle. Nothing, the backwards will not go any whole cycle. Backwards will go only one half. Because then it is not broadcast anymore. It's just dropped right there.
So for a packet to reach D, it can also go through A, C, D, and will be the same hop, right?
If packet goes to D, it will be sent to B, C, E, yeah.
No, from A to D, it goes from A to D. Can it go to A, C, D?
It will come, it will be dropped because I mean, okay, whichever makes first. It makes first. I mean, the thing is, here I have assumed that this is a shorter path than that one. I mean, it's arbitrary. Okay. All right. So route maintenance. Now here is some of the fine points. We have already said that, but we need to revisit. Each node keeps a list of active neighbors. Reply to a hello within a timeout. So even if you don't need anything, you hello. Hello, how are you? Hello, how are you? Hello, how are you? Just to make sure that you are alive and well. If you don't reply, if you don't get a hello from your neighbor, then you know they're gone. Okay. So I broadcast to all my neighbors, and I just listen to their hellos. Okay. Now it is quite possible that I'm sleeping, and so I may not get your hello. But when I wake up, then I will send an hello, and you will send hello, so I will be up to date then. Right? So while I'm sleeping, you know that I'm not there, and so no packet will be forwarded by me and nothing. If a link in a routing table breaks, all active neighbors are informed by route error messages. So now if suppose a packet was going to go to number node 2 and the number node 2 is down, then I create an error message and saying to all my neighbors, look, my friend is down. No, up to the point that we put the table. See, what will happen is after that answer is made by that so many 28 packets, at that point the packet goes and somebody on the way may be down. Then the route error will come back. Oh yeah, it's quite possible that the reply may not make it, and then the sequence number 2 will come. Then basically you will ask the second answer. Now what will happen is this. I mean, basically you got the answer from 10 and it was coming, let's say, I don't remember exactly the path, but let's say it was supposed to go through 5 and 5 is down. Now the answer will not reach 1. So one will send another request. Now it will say, this is my request number 2, please. I have the answer for 1 a.m., but I don't have any answers in that 1 a.m. But this is my request number 2. Since my request number 2, everybody will think that this is a new request now. So they will not discard it. They will forward it. While can I? Oh, well, it's not nice job. So the thing is, what it is that yes, if 9 was trying to reach 1 for whatever reason, then it will say, okay, to everybody, please, send me a path to 1. But right now it is just forwarding somebody else's packet and it drops it and tells everybody, sorry, there's no path to 5. Right? And since there is no path to 5, all the neighbors will know. Now what will happen is one will send a second request, and of course it will not go through 5, it will go through 1, 2, and 4, and then it will find the shortest path somehow. All right. So R error is also sent if a packet transmission fails. R error contains the destination sequence number that failed. Okay. So basically, remember destination sequence number. What is that? That's why I say I have the answer at 1 a.m. but not later. That 1 a.m. is the destination sequence number. So it will be in the reply or it will be in the response, and it will say that sorry, the request that you had sent at 1 a.m. is failed. When a source receives an R error, it starts the route discovery with that sequence number. So then it says, okay, all right, now we start again. Disadvantage is intermediate node may send more up to date but still stale routes. Now, this is another fine point to remember. That suppose you say I don't have anything since 1 a.m. So somebody has 2 a.m. right? And they may send you the answer, but that's no good. This is 5 p.m. now. So I have a better answer than you, but my answer is as bad as yours. But I'm going to send it to you anyway because mine is better, right? So that's the disadvantage in the sense that newer doesn't mean that up to date. It's just newer. Right? All right. So this is all documented in RFC 3561. If you want to understand this thing, I don't think RFC 39, that number, has this table kind of stuff. I prepared it myself. And so just, make sure that you understand this table. You have to prepare a table. Just take an Excel worksheet and start writing it. This takes quite a bit of time, very painful. And even after the third round, we found one error here. Duplicate discard should be blank. So, all right. Now, if there are any questions about EODB, this is a good time to ask because this is your homework, and I just want to make sure that people understand what homeworks are due. Today is Wednesday, so you will give 2 homeworks, 13A, which is just numbering. We have the R and L and C parameters that we wanted to see parameters. Put that in those formulas and number these things. The node C has an address of 20. Okay, and the second one is that the same network, exactly the same network that I had before, but now 2 is looking for the answer to 10. So 2 will start, it will send to all its neighbors and their neighbors and so on and so forth. Okay. Now, so before I go to the next part of the chapter, is there any question about these 2 homeworks? Huh? No, right now, so Saturday and Friday, whatever, Friday, Sunday. C is there, hopefully. So you can answer this thing, right? Okay. All right. Now, so I'm going to go to the next one, which is DSR. So DSR is a competition to AODB. Okay, and both are standardized by IETF. The way IETF works is that, if a lot of people agree, then they just write a method. So DSR and AODB are competition, and both are IETF. So DSR is on-demand routing using source route. Okay, so now this is source route. What does source route mean? Source route means that the packet does not just have a destination address. The packet has complete path in the packet. Okay, so it's like your airline ticket. It says that you will go from here to New York to blah blah blah, this city, that city. So whole path is in that ticket.
Not only the next.
Yeah, not only the next step, right? So uh, so most of the real world really follows the source route. I mean, if you get a bus ticket, train ticket, landline ticket, your routing is always source route. But I mean, if you were in a hurry, then you will say, okay, let me first reach New York and find the next flight, right? That would be what we do in the internet. You see what I mean? And so source route is the list of routers along the path are in the packet. Okay. And the routing database, you keep the complete route to reach and destination. So you remember the complete route. If you want to go to Germany, this is the route. If you want to go to Philadelphia, this is the route. And so on and so forth. Each entry has an expiration period and is timed out. So they put a lifetime on everything. If a route is not available, then we send a route request to all the neighbors, just like before. So the route request as follows. This is my source. I'm sending it to everybody. This is a route request. ID, request ID, and the destination address and the route record. Okay, so now let's explain these fields. This is simply saying that this is a request, not a reply. Right? Request ID is as before. Request ID is basically my request number 1, 2, or 3, whatever, right? And destination address is as before. I'm looking for 10. And route record. Now this is a big field. This is a big field in which now people will put the route. This is a request, right? In the reply, when it comes back, this will be all filled in. But right now, this is a request. So each neighbor adds itself to the route in the request and forwards it to neighbor. So you put yourself in this route record and you forward it to all your neighbors. Right? Only first receipt. If this is your first receipt, suppose you have already gotten this ID before, then of course you don't put yourself, you just discard it. If this is the first time you have heard from this source and this ID, then you do something. So on the first receipt, it does not change the source address, but when you send it to your neighbors, you don't change the source address, you don't change anything. You just put yourself in there, in the path. If a node knows the route, it appends the rest of the route and returns the return reply. If you know the rest of the route, so you're in New York and the New York guys know how to get to Germany, they will put the whole thing and send it back right away. It doesn't have to go to Germany. rrep goes back along the recorded path. The rrep is the reply, route reply. That goes back along this path which is in the packet. Right? All nodes record the path in rrep. So when it comes back, everybody makes a note of it. Oh, we know how to get to Germany now. You see what I mean? Is that this is the best path, not only for one, but for me as well, to go to whatever we want to go to. All nodes record the path in rrep and rrec, and multiple routes cached. And that's another difference, is that now we might have more than one route to Germany. Because when one was looking, we went through New York and we found it. When two was looking, we went to Philadelphia and we found it. So now we have many paths to go to Germany. Okay, and this is what the airlines do.
Mm. And we pick the shortest.
Eh? We pick the shortest distance. No, actually, these are all shortest distance. I'm sorry. These are all shortest distance. But, okay, so we never keep a longer distance path. Okay, yeah, we shortest distance. But if there's another one of the same distance, then we keep it too. When later on we can pick one, yeah. The thing is, here, so in the previous exam AODB that we talked about, there was no path to begin with, right? All we knew was the shortest link. I mean, to go to Germany, I have to go through her, or something like that, right? That's all we knew, and we didn't keep, if this and that at the same time, we didn't keep that information. So just one answer we kept, even if there were two equal paths. If you look at the picture, which is actually coming up again, there are many ways to go to 10, right? But we just got one by chance that this was whatever we got. I don't know, remember, but now we got just one. But if you were just looking for a 4-hop path, so this is 1, 2, 3, 4-hop path, there could be other possibility. This is a 4-hop path. This is a 4-hop path, right? So this method will keep both, right? I think time is, which is called DSR. And this is for the sake of completeness, because if you know AODB, you need to know DSR. And DSR is source routing. You see, it says dynamic source routing. So that is the keyword, is source routing. And source routing means that the source specifies the complete route. Okay. Whereas in the other normal methods, source just gives the destination and the network figures out the route. So it is a source route, and the list of routers along the path in the packet. There is a routing database for each node contains a complete route. So you will have in your routing table complete route to every destination that you will ever want to go to. Each entry has an expiration period and is timed out, basically. So this is true for any routing database. You don't want to use old routes. And if a route is not available, you send the route request to all the neighbors. So if you don't know, then you just basically send a RRQ, which is route request, RREC, to all the neighbors. You say, okay, well, I want to know about this guy, right? So you see the RREC has your address. The destination is broadcast, means it goes to everybody. Type is RREC. Again, we were talking about the request ID. This would be 1, 2, 3, 4, 5. Sequential number, right now 1. Destination address, who we want, number 10 maybe. And route record. This is a variable length field. This is where people will put the route. So each neighbor adds itself to the route in the request. So they add themselves here. And forward to all of its neighbor. Only the first receipt. So when you get the packet first time, you put yourself in the record and send it. Second time, you don't do anything. Clear? I mean, that is kind of obvious. And does not change the source address. Source address is still the previous source address. This broadcast is still the same RQ and request ID. Everything else is same. Right? If a node knows the route, it appends the rest of the route and returns a route reply. So now if somebody knows the route to the destination, then they don't have to send it all the way to the destination. They can send an RREP. Right? And that will have complete record. RREP goes back along the recorded path. Now, while the request is broadcast, the reply is not. All right. So the reply will have the address of the node that sent it, and then the broadcast. No, it will not be the broadcast. It will be to the destination and then to the source actually. And then this is the route record. We'll have the path. All nodes record the path in RREP and RREC. And multiple copies are cached. Multiple routes are cached. So you might have 2 or 3 routes, and they will all be in your table. So here's an example. node 1 sends rrec to basically 10. So our node 1 wants to know the path to 10. So it will send an rrec to 2, 3, and 4. 2 will send it back to again 1, 5, and 7. In this case, actually it is much easier not to send to 1 because the packet already says that I have been to 1. Right? So it will send to 2, 5, and 7, and so on and so forth. Let us see. To 5 and 7. Note rrec is not sent to 1 because it is already in the packet. It says it came 1-2. Right? And so even this 5 knows that it came 1, 3, 5. So it will not send back to 3. Right? It will just send, depending upon where it came from, it will send to everybody else, but not that back node. So, and node 3 sends to 5, node 4 sends to 6, and so on and so forth. And here is the complete packet thing, exactly following the same notation as before. So we have the packet in, packet out. So this is the sequence number of the packet, 1338, right? And this packet in is pointing to which packet we are talking about. So this packet 1 appears here. It was sent from 1 to 2. Right? Appears here. The same packet 1 appears here. It was sent from 1 to 2, but this time it is going from 2 to 7. Previously, it was going from 2 to 5. Right? So when packet is received at 2, this says this is a new one, and therefore it records and forwards. It records itself. 1-2, 1-3, 1-4, each of them record themselves in the packet. They also record the table. Okay, I haven't shown the table here, but 2 will have an entry which says if I ever want to reach 1, it is directly connected, which is kind of a straightforward. But as we go to 5, 5 will know that when I want to go to 1, I have to go through 2. See what I mean? So the new rrec, record and forward. I should have said record in the packet and record in your table. Okay, 2 recordings. In the packet you put yourself, and you put in your table the backward path. So the rest is actually kind of straightforward. 1 to 2, 1 to 2, sorry, not this one. Here, 2 to 5, 2 to 7, 3 to 5, 4 to 6. You can keep following. Okay. And now many of these are duplicates. For example, 3 to 5 is a duplicate, right? Because it already 5 has already heard from 2, so it will not do any action. Now here is the thing though, no, it will do some action. Reason it is doing same action is because even though it heard that request, it is same number of hops. So this is an alternative path of the same cost if you measure the cost by hops. Okay, so it will make a record in its table, and it will make a record in the packet and will forward. Okay, so duplicate, sorry, this one is duplicate ID, but same hops. Duplicate ID longer paths. So this, when it comes from 5 to 8, in this case, it knows that I have heard this, and I have heard before. This is not longer path. 1358. This is came from 3. Sorry, this one is 1358 is still same path. Yeah. So this one, the correct answer would be duplicate ID, same hops, record and forward. Right? Now let's look at something else. So this one, duplicate ID, now this is at 6. Right? Now 6 has heard previously hop 2. So it isn't going to, of course, discard all of these. And so these 4s are all going to be discarded. And let's see. Let's just see the last one, 9. 9 first hears with 3 hops, right? So all the 4 hops will be discarded, right? Now the only people who will keep this packet is 10, right? Now the thing is, since it is a new request, it will respond through that route. This is same hops, right? Duplicate ID, same hops, it will respond through that path. And this is duplicate ID, same hops, will respond to that hop. Okay, so 3 responses will come back.
Why is that?
Okay, through, okay, so let's see, through 10, 9, 5, 7, 2, 1. 1, 2, 3, 4. This should be 10. Can you write that down, please? And this is 7. The previous one is 7. This is 10. Good? All right, thanks. All right. And so the rest of them look correct so far. If you find any errors, let me know. And then, so all these RFs go back. Okay. So let's see. This is packet number 18 is right here. This is packet number 19 is right there. And this is packet number 22 is right there. 3 packets go back. Okay. Now they are just going along the single path and everybody is recording everything on the path. Okay. Finally, they will reach to 3 paths. And so 1 knows that I can go through 1, 2, 5, 9, 10, 1, 2, 7, 9, 10, 1, 3, 5, 9, 10. So 1, 2, 5, 9, 10, 1, 3, 5, 9, 10, 1, 2, 7, 9, 10. 4 paths. This path is discarded because it is 5. Only 4 hops path. This is 5 hops. So 4 hops are this one, and this is 5 hops. So 4 hops path. There are 3 paths. Okay. 1, 2, 7, 9, 10, 1, 3, 5, 9, 10, and 1, 3, 5, 9, 10. 1, 3, 5, 9, 10, 1, 2, 7, 5, 9, 10. There was one more. 1, 2, 5, and 1, 2, 7. 1, 2, 5 this way, and 1, 2, 7 that way. So you can see the advantage of DSR, except that basically, so I mean, like, this is all right. Route maintenance. If a transmission failed, route error is sent to the source. It contains host at both ends of the link. What this means is now you got the path and you send a packet along that path and suddenly find out that the airport at New York is down, or the path from New York is no longer available. You get an email back, or you get a request back saying that this is called route error. Route error back that that path is no longer working, and it is a packet that you sent to 10. All right. Now, so now everybody will make a note of that the New York is not working. So every path that include that link, whatever link was not working, are deleted from the whole table. Okay, along the path. Source may reinitiate the route discovery. Now, source may have another path. In that case, it doesn't have to do anything, just use the second path. If it doesn't have any path left, then it has to do another discovery. Caching multiple routes results in a faster recovery, but the routes may be stale, resulting in cache poisoning at other nodes. So let me explain those word by word. First of all, because you have multiple paths, you don't have to worry about doing the whole discovery all over again. All right, but it's quite possible that those paths you haven't used for 2 days. right? And therefore they may be stale. And third thing is it can result in cache poisoning. Cache poisoning becomes basically is that when you disturb or you make somebody else good cache bad, or you just make somebody's cache bad, doesn't matter. Is that somebody asks you what is the path to 10, and you say here's the path which is 2 days old, right? So they just use that path which you haven't used, they haven't used, and they will find out it's bad. That is called cache poisoning. Okay. The same name is used by the poisoning in DNS. So DNS is very similar. DNS is domain name service. When you ask domain name service, what is IBM.com? It will give you an address, but somebody can put a wrong address. Because they had a wrong address, they can tell their neighbors or somebody else who is asking that this is the address. So they have poisoned somebody else's cache. Okay, so that is what cache poisoning is. Not suitable for high mobility environments, and you really don't want to use where things are moving very fast. I mean, if things are stable, no problem. But if the people are moving, then you're going to fail quite a bit, and then it takes quite a bit to discover all these paths. Source route overhead in each packet, and each packet becomes longer and longer and longer. I mean, as it goes by. So, not only that, not only discovery packet, but even the original packet that you send, it has to have the whole path in the header. Every packet has the whole path in the header. Okay, and so that's an overhead. Anyway, this was all done in 2007, quite old. There's an RFC 4728. So, any question about DSR? Can you make this table? This is the next homework. See, now you're experts in making tables. So, yes, this is 2007. Well, I mean, here's the thing. I'm sure there is something new over there. I mean, like, the thing is, but what happens is after that, basically, if you ever need for your job, you know what DSR is, and then you go ahead and find what is the latest version of this thing. Okay, so right now you understand DSR, and that's good enough for this kind of thing, right? Now AOD versus DSR. In DSR, a single RREC results in several paths, routes to several destinations. Okay, so here's the thing. When the answer comes back that the path to 10 is 13579,957, then you know the shortest path to 9, you know shortest path to 5, you know shortest path to 3. Right? It is just not for 10. Everybody on that path is also on the right path.
I mean, okay, so it seems like you will then reply in all three possible.
Yeah, that was the point I made here. So 18, 19, 20 are 3 responses. Right? You send one request and you got 3 responses. Okay, so that's the advantage. In DSR, our error messages are sent to the source, not broadcast. So that is the decision that DSR made, that when something fails, you don't broadcast to all your neighbors that this has failed. You just tell the source. So maybe the people along the path will know, but other people will not know. Okay. Third is route discovery is delayed until all cached entries have been tried. If you have 3 entries, you're not going to do any more until you have tried 1, it failed, tried 2, and it failed, tried 3, and it failed. Then you say, okay, right now it's time that I get a new entry. So that time is so things are moving very fast. You don't want to use it. Okay, so routing table. This contains a route, and this one contains a next hop. Packet contains the route. The packet contains just the next hop. Replies. There are multiple replies only first. Route deletion is very fast and local. So let's discuss that in a minute. Okay, and here the route deletion is slow but global. So what happens is when one of your routes fails, you know it, but others may not. Okay. So if 9 through 10 fails, 9 through 10 fails, or let us take an example of 7 through 9 fails, maybe these people will know it, but other people who are going through 7 will not. Okay. And so that is, deletion is fast but local. Here you broadcast the errors, right? So everybody knows. And so there are advantages and disadvantages. Now, if you had the packet numbering like we talked about, if you remember, you did homework 10A. In homework 10A, you gave the route number, the node numbers to each node, right? If you do that, then the tree routing becomes very easy. Then you don't have to discover it because you know by the numbers. So all leaf nodes send the packet to their parents. Routing is very simple. When somebody wants to send something, they just send it to their parent and let them figure it out. Okay? They're all children, actually, not even adults. Okay? They're all children. Okay? Each parent checks the address to see if it is in the sub-range. Now the parents will say, okay, all right, I have the range from 11 to 13 or whatever, right? So is it one of my child that needs this one? If not, then I have to send it to my parent. Okay. So if you are sending a packet, let's say to 31, suppose 12 sends it to 31. What will happen? 12 will send it to who? 11. And 11 will say it is not in my range. So it will send it to C, 10. And C say, yeah, this is in my range. And I gave that range to R4, that part of the range. It will send to R4. R4 says, yeah, this is in my range. It will send to 31. The packet will go like that. So if you have the correct names, then you don't have to worry about routing and discovering and all that, because you can just do it by naming. Okay. Now you can work out the same way as to how the packets will go from 18 to 12. I mean, basically, same exact example. 18 sends to parent, and parent sends to C, C sends to R1, and it goes to like that. So example. So this is good. So many to one routing. Now here you think though, in IoT world, there is many to one routing, which is not common in other areas. But in IoT world, everybody is sending the data to a central point where it is being collected, right? So everything is going to G, which is the gateway, and from gateway to wherever it is going, right? So used for sensor data collections, all data goes to a concentrator or a gateway. Gateway has a large memory and hold complete routes to all the nodes. So now the gateway is not a little IoT device. It is gateway is a gateway, right? It's almost a mini computer. So it can basically keep that, okay, ABC is on this branch, DEF is here, H is there. So it can know exactly just like what we talked about. But each node only remembers the next hop towards the gateway. But each node actually basically all they remember is that their parent. Right? So if you do this tree hierarchical routing, then that's what people can just use and then make IoT very simple. The IoT device is very simple. The gateway is the one which is complex. All right, so these are all the routing methods which are used. In fact, we will talk a little bit more about routing in the next lecture. Okay, any questions about routing, AODB, DSR, or tree routing? Now, tree hierarchical routing is different from AODB and DSR. Right? AODB and DSR are true mesh routing. Tree routing works only if you have a tree and you have numbered the nodes, not randomly, but through this scheme. Okay, if there are no questions, then we move on to RF4CE. RF, radio frequency for consumer electronics. The consumer electronics is all these things that we have at home, like TV mostly. Previously, we used to have radio and tape recorders, but now all we have is the TV, right? TV can also act as a radio, because there are smart TVs, and can also act as, well, they don't really act as a tape recorder right now. But anyway, so RFCE. So basically, all these devices and the set-top boxes are also consumer electronics, and they need a remote. And for that remote, they used to have this infrared controls. And infrared is light, and therefore you really need to point it in that direction. So they said, why can't we get rid of that light and get wireless with the radio waves? And so they came to Zigbee, and Zigbee produced a version of its protocol called Zigbee RF4CE. Okay, and it operates in 2.4 gigahertz. Okay, and it uses these three channels. So basically, they basically felt that if we use these channels, maybe they will have the least interference on themselves and the least interference on others. Although I mean, I haven't verified it, because let's see, in Wi-Fi we use 4 channels at a time. So 1 through 4, and then you have to keep calculating. So I don't know where 15 will fit in, but it will be on the boundary of something, okay? And similarly 20 in the boundary of something, and 25 is in the boundary of something. So this is, and the maximum file payload is 127 bytes. So that actually is nothing new. That comes from 15.4. Okay, Zigbee, which is based upon 15.4, has to have 127 bytes. 2 types of devices. Now the devices, remotes and targets. So basically, TVs and DVD players, these are the targets, and your remote is the one, is the device, and they can both talk to each other. This is interesting part. Previously, you couldn't find a remote if you lost it, because TV couldn't talk to, I mean, couldn't send a message to remote. Remote can send to the person, but now they can. So you can press some button on the TV, and it will buzz the remote. Have you seen that? Have you done that? Have you used it? Not yet. But the same thing is used on the phones, or similar thing. Actually, I don't know whether they use Zigbee, but on my phone, I mean, we have this, everybody has this nowadays, this portable phone, but unwired phone. So wireless phones. And so if you lose the phone somewhere, you can press some button on the base, and the base pages the mobile. Eh? Well, so that one actually, iPhone, Find My iPhone is an app which uses, I don't think it uses Zigbee though, because there is no Zigbee in iPhone. It may use Bluetooth, but what it does really use is regular Wi-Fi. So this is what happens. If let's say I'm looking for my iPhone, which I have done almost every month, several times. And so I will take my wife's iPhone and say, okay, find my iPhone. And it will show me that iPhone is here in my house and not in my office. All right. Now we're in the house. That is very difficult to figure out, right? Because that accuracy is not there. So then there is a button which says, ask the phone to ring. And even if the phone ringer is off, even if the volume is 0, it will ring. And then I can go to that room and find the phone. It is not using Zigbee, but it's a similar concept. Similar concept is that by Wi-Fi you can do the same thing. All right, status display, and then the remote can just show the status of the target. So nowadays, remote they come. I mean, if you really see a smartphone, a smart TV, you can talk to the remote and you can say, okay, all right, turn to channel 5. Okay, they have a Siri-like thing, voice recognition. and they can talk to them, or you can just see whether the what channel is on, things like that. So there is a two-way communication between the remote and the target. Paging can look at them. We already talked about pairing. Now here you think though, basically the remotes and the TV have to be paired. Otherwise, you are trying to turn on this TV and that TV will turn on. So at the beginning, when you get a new remote, you have to do some process so that they learn each other keys and only respond to each other. Okay. Now I had more slides on RF4C, but I don't think it is worth it because RF4C is again quite old, and we all use it quite a bit now. So the next thing we want to talk about is zigbee 2030.5. I don't know why that name, but it was previously called zigbee Smart Energy 2. Okay, they had a zigbee Smart Energy 1, they had zigbee before that, they had zigbee Pro before that, and they said no, let's put a number rather than these alphabets. So this is 2030.5, and I don't know how 2030 came about, but that says something about version. Okay, so this is the key thing about 2030.5 is that it is a smart energy. Smart energy means low energy. Okay, you can monitor, control, and automatic delivery of use of energy and water. So even though it is low energy, it is also used by utility companies. Okay, energy and water. Adds plug-ins, vehicle charging, configuration, and firmware download. So now there is a new market coming up, and that is of electrical vehicles. Okay, so electrical vehicles, as soon as you park, need to charge them at your home, or if you can bring it here in Washu, we have several charging stations. You can charge it at your office, and so that is called plug-in vehicle charging. Okay, configuration and firmware download. So when you park there, something talks to something and says, okay, this is Rajan's car, charge it, for everything that, they use for a whole day, they're charged so much money, so it will show up in my account. Okay, if you come to my home and park your car on my charging place, it won't charge unless I do something. All right, so that is what it means is plug-in vehicle charging, configuration, and firmware download, and also because it is communicating, that can be used for firmware upgrade. So if you want to change something in your car's software, you can do that through that interface. It's just like your phone, once your phone is wireless, you don't have to connect to anything to upgrade it. You can say upgrade, and then it will come by Wi-Fi. And
So usually you must have internet connection.
well, no, see, the thing is, okay, so the reason it doesn't need internet connection is because the car is one end and you're talking to something that is on the ground. Well, it doesn't have to be. It may need to be, but it may not need to be. See, the thing is, if you are going to Washu, of course, if they're going to charge, they are probably going to send it to some office in Washu, which needs some connection to that office. And if it was government owned, probably it goes to government office. How does it go to government office? Now it doesn't need to be the complete internet. It could just be directly connected to internet. I mean, having said that, most likely it is going through internet because who is going to have single wire coming from that to this, right? So everything is just broadcast to the network on the campus. Campus networks takes it to the place it's supposed to go. If it needs to go through the internet to another campus, so it might go. So the internet connection is not the key. The key is the connection. Connection between two devices. So here, when I do remote, and my remote and TV is another example. My remote and my TV, they don't need internet connection. In my case, actually, the TV does have an internet connection. Okay, because it talks to Netflix, it talks to whatever. I mean, I don't know what it is, YouTube, and other things, right? So it's a smart TV means it is connected to the internet. That's what smart means.
Mm-hmm. In this case, is that a plug-in vehicle charging, so you have to physically plug in.
Okay, so there are two kinds of charger. Okay, I mean that word plug-in may be a little bit misleading, but there are two kinds of charger. There is wireless charging.
I know.
No, so the thing is, okay, for cars also. So there is wireless charging and there is wired charging. Wired charging would do much faster. You would be charged in, in few hours. Wireless charging will probably take you overnight or something. But again, it is convenience, right? So I don't know how many of you have gotten a wireless charger for your phone, but they're available. I have never gotten it because I never felt the need for it. I just plug in a wire and go to sleep.
Yeah. So you want to do a wireless charger.
Yeah, yeah,
It will take us for life.
yeah. Okay. So that is not the charging part which is we are talking about here. We are talking about the configuration firmware download and the money charging. The electrical charging is
Yeah, I mean, but if you're using ZigBee, it has to be wireless, right?
huh?
If you're using ZigBee,
For not power charging. It has to be wireless for communications. See, there are two concepts here: communication and charging. Now, the charging is electrical power charging, and charging is money charging. Right? You need the communication. Eh?
so battery is also with the charger. So like
That is the power charging. But the batteries need power charging, but the person who's supplying the power needs money charging. That is accounting
basically just the two devices connect to each other with 3.55.
for communication.
Yeah.
They're connected to each other for communication. Power will not go through Zigbee.
Okay. So the communication to make it.
No, power is a totally different circuit. Power is a totally different circuit.
Yeah, I mean, just my point being, so if you use a wire charging, it doesn't really need it because you're plugging.
No, hold on. No. So it is quite possible. So your question is for power charging, do we need accounting? The answer is yes. Okay. How that accounting is done, you could have in your power charging port an Ethernet connected, and then you could be doing wired communication. When you're doing wired power charging, you could have wired communication, or you could have wireless communication, even with wired charging. Huh?
You can do wire, so it should be much faster and efficient than the wireless.
Okay, all right. So that's a personal opinion. Okay, all right. Let's leave it at that. Okay. Any other question? Developed in collaboration with other smart grid communication technologies. So smart grid is all this about electrical communication. Yeah. It can do what? It can take your IP address. Yeah, I mean, it might give you an IP address. Who knows?
No. I mean, for example, like in a classroom, right, with a lot of computers, every computer maybe has the same IP address.
No. Hold on. So let's just see one more. So let's just this is a confusion and nothing to do with this lecture here. The question is, if you have multiple people in the room, they can all have the same IP address. The answer is no. Everybody, if they're connected to the same IP network. Now here's the thing, you could be connected to different IP network. Let me tell you how it is. So for example, I have in my office one router which is giving out the addresses on 192.168.0.1. Okay, so a lot of my computers have first three numbers same and then 1, 2, 3, 4, 5. I could have another router in the same room and it is giving out the same addresses, but these two networks are not connected. Right? They're wired and they're totally independent. They will work, but as soon as they're connected, there will be a lot of confusion as to which 192.168.3 you want to talk to. Right? So for example, in WashU, all the computers will have a different IP address. Otherwise, you would not be able to go from here to there if they have the same IP address. How do you talk to somebody who has the same IP address as you? right? So in a classroom, even if there are 2,000 people, there are 2,000 IP addresses, right? And nothing to do with Zigbee, but that is basically addressing. Addressing is same thing for MAC addresses. If everybody should have a different MAC address, if two people have the same MAC address, IP will not be able to distinguish them. It will send the packet to both of them. Yeah, yeah. No, no. So the thing is, now let's talk about this. There are two classrooms in two different parts of the campus. Okay, and both of them are using private addressing. Okay, so they can give the same address. Now, what will happen is this will work though. What will happen is you will get out of your private network. You will get onto the internet with your unique address, with your unique one address that you have from the internet. You will go to the next place with their unique IP address, and there it will be delivered to the same address. But on the internet, the packet is going from this unique IP to that unique IP, and then once it reaches there, it is given to the local private IP. Okay, so this will be done using some kind of encapsulation, something. Anyway, so that basically, yes, that will work. They can have the same address, but in the same room, it will be difficult. I mean, you can probably do the same thing in the same. I don't know how you do it, but basically, in the same room, it will be difficult to have overlapping IP addresses, and particularly if they're wireless. No, no, Zigbee is going to work. So the thing is, Zigbee case, basically, I think they're all going to use IPv6. So everybody is going to have their own IPv6 address. Okay. And it is not the IP address which is being charged. After you get the IP connection, you give your name, phone number, credit card number, and everything else. That is what is going to be charged. Right? So if somebody saw your IP address, they cannot just charge your IP address. I mean, they have to know that other things which are encrypted. Now, the problem with this 230.5 is this is IP based, and therefore it is incompatible with previous Zigbees. Now, this is a change of thinking now. What happened was previously Zigbee was based upon their own addressing and their own thing. They did so much work on this addressing thing. Remember this tree routing and giving the addresses, stochastic addressing, and this and that. And then they realized that if we forget all that stuff and give everybody this IPv6, then we don't have to do any of that complication. Everybody could come with their own IP address. You can make an IPv6 address from your MAC address. Okay, and you can just send the packet straight through. You don't need a hub or gateway or anything. Just you talk on the internet directly. So that is what this Zigbee is all about. Okay, it gets rid of most of the original Zigbee stuff and gives it to IP. Okay, so this is called Zigbee IP. Zigbee IP is the latest one. It uses standard IPv6 frame format. Now, I did not go through Zigbee frame format for this reason, because Zigbee has a frame format. When you take IPv6, IEEE 802.15.4 packet, it has a MAC frame, and then you put a Zigbee header on it. Now they don't want to do any of that. So they just go straight to IPv6 frame format, and that way you can connect sensor directly to internet without gateways. It uses PHY and MAC, and then uses this Zigbee IP thing with 230.5 that we talked about. IPv6 headers are so big, okay, because each address is 128 byte, 16 byte long, 128 bit, 16 byte long. So they have to compress it using 6LoWPAN. So we'll talk about that protocol. And RPL routing to discover topology. And people are coming and going, so how do you know who is where? So RPL is used for that, and we will talk about that too. And all internet protocols, UDP, TCP, HTTP can be used. Once you're on IPv6, you don't have to worry about any application layer protocols, profiles. So all that business about profiling is going away. Okay, because now you can use whatever you want. Multicast forwarding, service discovery, etc. can be done by standard IP. Security using standard protocol, TLS, EAP, PANA, whatever. I mean, like these are all the security protocols. They can be used. So you don't have to, what they call, rediscover the world. Okay, IPv6 already there, the transport protocols are there, applications are there, the security is there. Just use that. So this is where they are coming back. And therefore it is not compatible with other versions of Zigbee since they use a different network layer frame format. Their frames are very different and need a gateway between Zigbee and Zigbee IP. So now, while the Zigbee IP sensors don't need a gateway to go on the internet, but if they want to go on Zigbee, they need a gateway. You understand that part? Because the previous Zigbee is not. All right, any question about Zigbee IP and 2030? Basically, the new thing is that they got rid of whole network layer and put IPv6. Now, we are going to move the topic to different thing called Z-Wave. So Z-Wave starts with Z, so a lot of people confuse that it is Zigbee. It is not. It has no relationship to Zigbee. It's a proprietary protocol, and actually, if you search for Zigbee on Amazon, which is I did, the day before preparing this Zigbee lecture, half of the devices were Z-Waves. Okay. Now Z-Wave will not work with Zigbee. Zigbee will not work with Z-Wave, so don't even get confused. You will need a gateway between them, right? And so Z-Wave was originally a proprietary protocol developed for remote control, now used for IoT, and now standardized by Z-Wave Alliance, which is different than the Zigbee Alliance. Okay, usually the same band 915.868 which Zigbee uses, and many IoT hubs support Z-Wave along with Zigbee. But this is, so here's the thing though, Z-Wave is very popular. Okay, it is as popular as Zigbee. So every hub that supports Zigbee also supports Zigbee. I mean, I don't say every, I don't know, at least my hub does. So my hub does Zigbee and Z-Wave both. Okay, but we haven't talked about Z-Wave. So if somebody asks you what is the Z-Wave, you say, well, I mean, I know it's a but we haven't talked about details of this. This is another protocol. That's all I want to make sure that at least you know that this is not Zigbee. That brings us to the end of this module, which actually kind of longer because it took 3 classes. But here are the key 6 points. It's an IoT protocol for sensors, industrial automation, and remote control using 15.4 Phi and Mac. Right? The Pro added some support, particularly for routing, fragmentation, and mesh topology. They developed a number of application profiles, just following the Bluetooth kind of things. An application support layer provides data and command communication between application objects. And so the application support layer, actually, if you remember the protocol stack we went through Zigbee, there was the APS before the applications that provides the things which are common to all the applications. And the network layer provides addressing and routing. Addressing can be assigned using distributed or stochastic schemes. We talked about how to give numbering. Routing is done by ODB or DSR or tree hierarchical or many-to-one routing. And then we talked about 2 special forms of Zigbee. Zigbee RF4CE, which is for 4CE, which is for remote, and Zigbee SEP2. I did not use the word SEP2, but this is a smart energy protocol 2. We talked about Zigbee smart energy. So SEP is smart energy protocol 2. All right, and Zigbee protocols are designed specifically remote control smart grid, and then Zigbee IP has come in, which uses standard IPv6. Okay, can you write a comment about Zigbee IP to be added to summary? All right, so you have done the homework A and B, and now C is same thing. Basically, you have to do DSR from 2 to 10. 2 wants to know how to get to 10, right? And we know that the shortest path is 279. 259, and that's it. You will probably get 2 paths. right? But you have to write down all the entries to figure out that.
So one thing would be
Yeah.
zigbee sub2 needs to be under the slide.
No, sub2 is okay, but zigbee IP was not on the list. Okay, any questions about zigbee? None, then we move on.